Okay, I'm Dora, and my Chinese name is Li Yuxun, and let's explain the question 1. Chapter 15, practice 8. The question is, show that it is executes as HM with angular frequency. This. So, the system is a block. When the block of density low B floats on the fluid of density low F. So, when these systems reaches equilibrium, the net force is 0. So I suppose that when an external force, this one external force, is applied to the block, it will move downward by x, and its buoyancy will increase that external buoyancy. So we only need to calculate this increase and prove it using simple harmonic oscillations. So the external buoyancy will equal to A times x times low f, where this is stands for excess liquid weight in displaced volume of block here, like this, n times g will equals to external buoyancy. So when m, the mass of the block, is equals to low b times a times h. Ah is equals to volume of block. So the delta f means the external force will equals to a times negative x times low f times g, like this. And because the external buoyancy is upward and x is downward, so we represent x is negative, and will equals to ma. M is equals to this, dou b times a times h, and times, we taking the second differential of x will equals to a. So this is second differential of x. And we eliminate a, and we will get the second differential of x will equals to this, negative low f times g over low b times h and times x. And when the system is simple harmonic oscillations, we can represent x like this. X will equals to amplitude times sine omega t plus theta. And when we take the second differential of x will equals to negative omega squared times a sine of omega t plus theta. This will equals to x. So when we look these two are the same, so we can say that this one will equals to omega squared. So omega squared will equals to low f times g over low b times h. So we can get the omega will equals to the root of low f times g over low b times h. Okay, let's move to chapter 15, problem 13. So it says we have to estimate the period of the oscillation for the Earth, and I draw this ball here, and this ball will experience a centripetal force like this. Since we only need the x direction component, so we can decompose the centripetal force into a component in the x direction that equals to f sine theta, and f sine theta will equals to f times x over r, like this. So from problem we get f will equals to mgr over big R. So we substitute this in here, so and times x over r, we can eliminate the r, and we will get this negative mg times x over r, and this will equals to ma, like m times take second derivative of x, and we eliminate m, we will get this. So like the question last one, SHM, we can know that x will equals to a sine omega t plus theta. So the same. So after look at this, we can get omega square will equals to g over r. So omega will equals to the root of g over r. So the t is this, t will equals to 2 pi over omega. So we substitute this in here, we can get the period will equals to 2 pi times square of r over g. Yeah, okay. Next question is chapter 16, problem 6. So it says a rope of mat and then L hangs vertically, show that time needed for a post to travel from the bottom end to the support is T equals to this one. And T means the tension of the rope at any point on the rope. So I consider a short segment of the rope x meter from its lower end, and the length of the rope below its segment is x, and its mass is equals to mu times x. The mu means the rope density, and the rope density will equals to the mass of the rope and over L, the length of the rope. And the tension here will equals to m times g, where and m equals to mu x times n times g. Okay. So for a rope with changing tension, the local wave velocity is equals to the root of this one is the tension over mu, and it equals to the root of g times x. So the time required for a wave to travel along density dx is dt. Dt is equals to dx over v, the velocity, the wave velocity, local wave velocity. And we substitute this in here, we can get dt is equals to dx over root of g times x. So the total time, we can take the integral. I integrate x from L to 0, and L means from the bottom of the rope to the top is x equals to f, and bottom is x equals to 0. So from L integral to 0, we can get this, and finally we can get the answer. The period of time equals to this. And okay, the next question is chapter 16, problem 12. Problem 12, we have to use the problem 11's equation here. So the string density, the same as this one. The string density will equal to mass over L, the length of the rope, and we can get the answer of the rope density is 3.33 times 10 negative 3. So our fundamental frequency equals to this one. So we can calculate the fundamental frequency. After calculating, we can get the fundamental frequency will around and equals to 204 Hz. And by use the E is proportional A squared. A means amplitude, so amplitude will reduced by 10%. So A1 equals to 0.980, and the energy proportion will equals to this A1 over A0 square. So after calculation, we can get the proportion is 0.81. Therefore, the energy is reduced by 90%. So the delta energy equals to 0.19E0. So 15% energy loss is because the energy of sound equals to 0.5 times this gap of energy equals to 0.095 E0. So this energy is released in 0.1 seconds. So the power average, the question is the average radiated power. So the average power equals to the energy of sounds over 0.1 equals to 0.95 E0 over S. So we use the equation of problem 11, this one, we can get this. E0 will equals to mu times 2 pi f1 times A0, take this square and times L. And after calculation, we can get the E0 is equals to 3.28 times 10 and 10 of negative 3. So the P power of average is equals to this one, 0.935 E0, and it will equals to 3.1 m watt. And the remaining 50% of the energy is converted into internal energy, like friction or thermal energy with industry. Okay, finish. Thank you.